Yeah, so let's get started. So today we're talking about why StarRocks joins very fast, and we're gonna talk about why do we need fast joins and what is wrong with denormalizations, especially in real-time analytics, right? And we'll dive deeper into why StarRocks is fast. So it's not going to be very technical, but it's going to touch some of the technical aspects of how a query is run on the database in the database on a pretty higher level, right? And so it's going to be fun. So first, we're going to talk about how does a query work, right? From query planning to query execution. And then we're going to talk about query planning and what does it take to generate an optimal or a good query plan, right? And then we'll talk about the compute architecture and how different compute architecture can affect the performance, stability, and scalability of join operations, right? And then we'll touch a little bit on the query execution, right? Why OLAP databases now they run so fast in general, right? Okay, so here let's get started. So why do we need joins? And why denormalizations are kind of harmful, especially in real-time analytics, right? And by the time when database management system was invented in the 1970s, it's always been a good practice to keep your data in its most natural and original format, right? In a like multi-table format in Snowflake or Star Schema, right? And it wasn't that long ago until that's not the case anymore, because a lot of the OLAP, the real-time OLAP databases, simply do not do joins very well, or they didn't even have join in mind when they design and implement the system, right? And they actually rely on the users, us, uh, to perform a thing called denormalization. Denormalization basically means you pre-join your multi-table schema tables, like normalized tables, into a denormalized table, which is a flat table, right? Before the data hits the OLAP database, right? And that can be a pretty harmful thing for several reasons, right? And especially for real-time data analytics. So first is that those pipelines are not really that easy to maintain, especially like with the time constraint of real time. And doing that in batch with a Hadoop or with a Spark job, runs for hours, and it might not do a batch job, might not be that complicated, but doing that a stateful stream processing uh, job, and that can be a pain to implement as well as to maintain, right, and to configure, right. And it requires a like an infra level software, additional infra level software on your data pipeline, as well as requires much much more labor and manpower to actually code and engineering effort to make that happen, right. And the second reason is it really locks your data into a single view format, right? So when you do denormalization, you have to know your query pattern beforehand because you're pre-joining everything into one, right? And it's really difficult to adapt to business change because it's simple. Let's say changing a data type of a column, or adding a column, you have to backfill, you have to reconfigure your entire pipeline and backfill all of your data, right? And let's take an example, like one of our bigger StarRocks users is Airbnb, and they have a Minerva platform, and it holds around 6+ petabytes of data in it. And before they were using Druid, Apache Druid, to do as a query engine and the storage engine, right? And the problem with Druid is that it does not do join very well. So they needed to denormalize everything, right? Everything into big flat tables. And because it's a metric platform, it stores thousands of metrics. And doing a metric, like changing a metric or adding a metric, is not really a big ask, right? But with the denormalization pipeline, it's really a big ask because reconfiguring the pipeline and backfilling the data can take somewhere from hours to even days, right? Because at the scale of data they're operating on, and plus the labor and plus the hardware resource that's being wasted. And it's a lot of overhead they're dealing with. And then they move to StarRocks, right? Because we can do on-the-fly join. So these are not the problem, right, anymore. So they can maintain the same data schema in their OLAP database, same as their data source, right? And so this problem is the reason why, part of the reason why we built the StarRocks project. And StarRocks, one thing I can count on StarRocks is that it can really do join well in the market. It's probably one of the, or the fastest in the market right now, right? And let's take a look at some benchmark first before we dive into the technical details. So first, this is a SSB benchmark test, right? And this actually has two variants. So there is the original SSB test. It's actually multi-table, right? And ClickHouse, the folks at ClickHouse made a variant of that. So they did a denormalization of the SSB benchmark into a SSB, we call it flat, right? And so it's just the SSB, but without the join part. And the join operation is expensive, no matter how optimized your engine is, right? And so here, let's look at some results, right? On the right-hand side, you can see 4 different colors, right? Everything with the flat is run on the variant that is denormalized. So the first 3. And StarRocks is the fastest out of all. But the key thing is with the last one. StarRocks multi-table is actually faster than Druid's flat table, and it's almost as fast as ClickHouse flat, right? And this is a big thing because this alone can say that, we can really eliminate the whole denormalization pipeline without losing much, right? And StarRocks is really an engine or a database that's really designed to scale, especially with complex operations. It does better than most other solutions. I'm gonna go into the details later, right? And so this is the SSB benchmark. So the SSB benchmark resembles more like user-facing dashboards or reports, or some scenarios where the query is not like crazy out of whack, crazy complex, right? And yeah, and let's look at something that's more extreme, right? For the TBCDS benchmark test. And so TBCDS, I would say, is more, the query resembles more like those more complex ad hoc queries on the data lake, and those really complex ETL queries, right? Your data transformations and long running queries, right? And we did a comparison with Trino, right, on the TBCDS 1TB test, and that's querying external data, right, as a query engine. And StarRocks is 5.54 times faster than Trino on TBCDS, which is the kind of workload that Trino is best on, right? And yeah, so we talk about a lot about the problem and how well we can do it, but how do we achieve good multi-table query performance? So going to that, we need to, let's set some foundations, right? Let's take a look at how a query work from the SQL query to the result, right? And this is really a bird's eye view. And this actually works for most of the databases out there because it's really high level. So you have your SQL query, right? And it hits a network layer. And the network layer sends a SQL query to your planner. And your planner reads a SQL query and try to understand it and come up with a physical plan, a physical distributed plan for our case, right? And the plan is sent to the execution engine, and the execution engine scans the data from the storage engine, right? If it's with predicates, hopefully the predicates can push down so it doesn't scan all of the data, right? And that's the ability of your storage engine, right? And gets the data, and according to the physical plan that's generated by the planner, the execution engine computes the result and return that to the user, right? Even on a higher level, a very high level, this is still a multi-layer process, and it requires all of the components to work with each other very well to achieve good scalability, stability, and performance, right? And on the right, you can see some like smaller components uh, of each like bigger part, and probably gonna go into detail with some of them later, right? And then first, let's look at query planning and what it takes to generate a good query execution plan and how StarRocks does it, right? And let's take a deeper look into query planning. This is kind of like a higher level, like a flow chart of how a query is planned in StarRocks. And this is actually pretty generic too. And a lot of the other database work like this as well, right? And yeah, so your SQL query hits a parser, and that's being converted to an abstract syntax tree, right? And it goes into an analyzer and it binds metadata and check if the SQL is legal and handle all the aliases, right? And then it's being transformed into a logical plan, and then further rewritten for like expression reuse and predicate put down, push down, and a lot of different things. And then it goes into the optimizer and generates a physical plan. And then the fragment builder generates a distributed plan for the execution to use, right? And I think the thing to talk about here is really the difference between logical plan and physical plan, right? Logical plan is, I would say, is more of what the query is trying to accomplish, and physical plan is how is it accomplished, right? And so we have a lot more control on the physical plan part. So which makes the optimizer a very like key component, or the one thing that actually can make a huge difference, like the biggest difference in the whole pipeline, right? And we're gonna go into the StarRocks cost-based optimizer. We have a cost-based optimizer, and like to optimize a query from it's like picking a route from point A to point B, right? But the search space is a lot more than you see on Google Map, right? And the search space of of like different ways to execute a query is enormous, right? Just for like join reordering, and is exponential to the number of tables that you're joining together, right? And you have different type of join algorithms, and you have different types of join strategies on the network level, right? And subgroup rewrite, and a lot of different things. So the search space is enormous, right? And the difference between an optimized plan and an unoptimized plan can be like several orders of magnitude big. Sometimes I get, like in the beginning, like earlier, get a SQL, from the customer. Our optimizer does something stupid, and the response can be minutes, right? And with a simple tweak, it can be sub-second. So the difference between the two are really big, right? Which makes optimizer a very important piece of the whole infrastructure, right? And so what does a cost-based optimizer do? Instead of like using rules and heuristics, predefined heuristics and rules, and to say which route to pick, so our cost-based optimizer actually collects statistics and compute the cost of each possible query path or query plan, and use a greedy algorithm to pick the best one, right? And the statistics collected are like min, max, like percentage of null, and how big the rows are, and those kind of statistics, right? And this is proven to be a much more efficient way of, although a lot more difficult to implement, but a more efficient way of generating good query plans, right? And yeah, it's based on a lot of things, right? It's based on the statistic from your storage, and it's based on the behavior of your execution engine. So it's strongly coupled with the execution and storage layer, right? And that's why our cost-based optimizer is natively built, and it's been optimized for a very long time, right? So I think the thing for a cost-based optimizer, for any optimizer, is that it's impossible to get it on the first try. And that's true for us too. I mean, for the CBO, our first release, it wasn't turned on by default, and we experienced a pretty long period with our seed users. They report a bad case, and we optimize, and our gain is based on our seed users suffering. But yeah, but thanks to the community, and thank God we're open source, and we can get this as efficient as it is right now. And that wasn't a easy process, right? And this is our cost-based optimizer. And one other thing I want to touch on is data pruning, right? So, and this is part of the FE's job as well, and a little bit of that is the CBO. So, yeah, so it's called a global runtime filter. So what it does is it minimizes the number of rows or the amount of data the CPU needs uh, to to deal with, like during the execution, right? And let's look at that through an example, right? Okay, so we have a query here. Select all from fact table, join dimension table on fact.dimension ID, blah, 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 right? And the where clause, the predicate is on the join key, right? And the predicate is on the dimension table, right? And its price greater than 100. Right. And without a runtime filter, normally how would you run it? Right. So the left, because there's no predicate for the left table. So you just take all of the 1 billion rows and send that to the join operator. Right. And does what it does. And on the right hand side, because we have a predicate, it's going to get pushed down to the storage layer. So it's not going to get all of the data up. Right. Probably 1,000 rows and do the operation, right? So what if there's a way we can push this this predicate or this where clause to the left table as well, right? And it's probably going to filter a lot of the data. So in this case, let's say it's 1 billion rows to a million rows. That's many orders of magnitude less data the CPU needs to deal with, right? And yeah, this sounds pretty simple, right? Actually, in a single node or in a single node environment, it's not so complicated because there's no network that's associated, right, with this, right? But in a distributed environment, it's very different because we actually need to send this filter to all of the nodes that the other table is on, and this has a lot of network overhead. So the actual question or actual challenge is that, is the filter worth the network cost? Sometimes it is, sometimes it's not. And this is another like a CPU story all over again, right? It needs a lot of optimization. And we've had this feature for a pretty long time now, and it works. Yeah. And then let's look at compute architecture, right? And this is where I see some of the biggest difference between us and a lot of the real-time OLAP databases like ClickHouse and Druid, right? How we handle join operations. And this is a key that why our join is able to scale, right? Let's look at some different architectures first, right? I kind of on the high level summarize them into like three categories. So first type is scatter gather, right? And so you have a bigger task and you distribute all of the tasks to different nodes, and they do their part and take the intermediate result and gather it in the larger node, right? And then return the result, right? And this kind of queries execution is easily bottleneck on a single node, right? Because everything converges to one, right? And this is especially not suitable for join and high cardinality aggregations at scale, because like for scatter gather on join, like for other OLAP real-time OLAP databases, they do not support data shuffling, right? And they depends on other kinds of methods that are more scatter gather. So creating a single bottleneck, easily create a single bottleneck in the whole cluster. I'm going to go into the detail later in like 2 slides, right? And then the second one is kind of like map reduce, right? And map reduce is used a lot for those ETL jobs, right? So you have an operator, and every operator has a mapper reducing it, and all intermediate results are persisted to disk, right? And because everything is persisted, so it can be incredibly uh, uh, stable. Not is that it doesn't crash, is that if say you have a task that runs for 5 hours, right, and it breaks on the third hour, and you can always go back because all of the intermediate results are persisted to disk and go to the last checkpoint and resume your task. So this is great for those like long-lasting ETL data transformation workloads, but this does introduce a lot of performance overhead. So it's really not that good for sub-second or even submitted queries, right? And also, this kind of operation introduce wait time before different tasks. Right? And then let's go into the MPP architecture. The biggest difference between MPP and MapReduce, I would say, is MPP has the option to go completely in memory, and it supports shuffle operation between uh, the memory of different nodes, right? So everything runs really fast, and it actually scales, right? And because it use a pipeline execution kind of framework, so every time a query hits the database, it creates a kind of like a DAG or like a tree-like graph, and with all of the tasks on it, and all of the tasks can run at the same time, right? And this kind of architecture is what StarRocks is based on, and it's great for sub-second joins and aggregation at scale. So let's take a higher level look on the StarRocks architecture, right? As first of all, from the top to bottom, StarRocks supports MySQL protocol. So you can take your favorite BI tools or your application you already built, as long as it supports MySQL protocol, standard SQL, it's gonna connect to StarRocks, right? And we have an FE and a B. So the FE is your catalog manager. So it manages your metadata, and it does the query coordinating, right? It's like the PM of the of the query execution pipeline, right? It dictates like what query plan we take, the cluster takes, right, and send that to the B. And B is the execution engine, and can you be used as a cache, or it can be used as a storage engine, right? And it does all of the heavy lifting, right? And the first thing about StarRocks is MPP. And there's actually one thing I want to say beforehand, is that it's one little myth to debunk, right? I see a lot of talk online that MPP means strongly coupled storage and compute, and that's really not the case. Right? StarRocks features, storage and separated compute design, and from version 3.0. I think MPP is that it really stands for, it's parallel processing. So you have the ability to scale with whatever workload you're trying to do, right? And we're OLAP database, and we're trying to solve OLAP. So a lot of group by and join. So, and we can scale group by and join very well. Makes us MPP, right? And StarRocks, one key difference or key feature of StarRocks is it supports data shuffling, and we support many distributed join strategies. I'm gonna go deep into detail in the next slide, right? Because we have the option to go pure memory, makes us very good for low latency, large scale join and aggregated queries. As long as you add more nodes to it, it's gonna run faster, right? Okay, now let's take a look at how to execute joins at scale, right? Uh, First, we want to understand that a single node join is very different than distributed join, because distributed join brings much more overhead to the whole system, and planning a single node join is very different than planning a distributed join, right? And here the thing we really want to touch on is the join strategy, and that's different than the type of join we talk about, like left join, right join, or like inner join and as of join, those kind of joins. And it's also different than the join algorithms that we talk about, right? Like nested loop joins and hash join and merge sort join. So this is more on the network level, right? And distributed join operation, one challenge of it is to distribute the data to all of the related workers, right? And so there are two things we absolutely want to minimize. So first is the network utilization. So we want to minimize the amount of data that's being transferred between nodes. And also we want to minimize the data that's being processed in memory. So we don't want the same data in two nodes memory or two or more nodes memory. And we don't get two times of performance, right? And what is data shuffling and why is it important? It's data shuffling is a way to shuffle all of the data to your worker nodes based on the join key, right? And this is one way to enable truly scalable distributed joins. And I'm gonna have 5 examples to kind of talk about this in more depth, right? So in our example, we're gonna have two tables. I'm gonna go through each one by one, right? And table A and table B. Let's say table A is a bigger table, has 5,000 rows, and table B is a smaller table, smaller dimension table that has 1,000 rows, right? Let's look at different join strategies and what shuffle can offer and what other choices do we have, right? And first, I want to kind of categorize joins into two categories. One is kind of like local join, and one is like distributed join. I'm not even sure that's the right name, but yeah, but for easier to explain, right? So local join is that requires a certain data distribution. So during the join operation, you don't need to move the data around, right? And for a distributed join query is that it does not require a certain data distribution beforehand, and you move the data on the fly during the join operation, right? And let's look at some different joins. So first is collocated join. And actually, a lot of people call this local join, right? And this actually relies on both table to be distributed on the same join key, when before the data is ingested, right? And yeah, so if everything is on the same distributed on the same join key during the join, there's no need to move any data around, right? So each node can just do their part of the joining and gather the result, return it, and that's all, right? And and this is very fast because there's like no network overhead. Everything's done completely locally, but it makes join kind of rigid, right? This is like the denormalization problem all over again. So you need to absolutely know about the query, what you want to join beforehand, and you actually need to like pre-configure that before ingesting the data. And if you want to change that, you have to like ingest all of the data. It's fast, but it's not flexible, right? Co-located join it's a great way to accelerate your query if you know what your query is going to look like, right? And second type is another localized join, is replicated join. So what this is that it replicates the right table into the every single node that the left table is present. So let's say we have three, right? Three compute nodes. So you have three copies of your table B in the your whole cluster, right? And for this, yeah, because all of the data is distributed in all of the nodes, there's no network overhead, right? So join is completely local, but it wastes a lot of storage space, right? And this is fast as well. And then let's go into some distributed joins. So the first one actually does not require data shuffling, but there is a trade-off to that, right? And the reason why I talk about replicated join is actually, I want to actually talk about broadcast join, because broadcast join can be understood as a kind of like an on-the-fly replicated join, right? And so during your query execution, you broadcast the right table to all of the nodes that your left table is present, right? It really depends on how many nodes your customer have, right? And but the problem with this kind of operation is that the network and memory usage does not only scale with your data size, it also scales with the size of your cluster. So the bigger your cluster, the more network it's going to use. And the bigger the data size, the more network it's going to use. So yeah, so it's really not really that scalable, and it's very useful for like smaller clusters or joins with a very tiny right table, right? You have a big fact table and a small dimensional table, and you join the two together, and this is gonna work okay. But for two like larger table, for if the right table is larger, you're gonna run into a lot of network and memory issues if this is the only type of distributed join you support, right? And now let's go into the shuffle join, and this is what StarRocks supports, and this is what StarRocks mainly rely on in a lot of the the on the fly join kind of scenarios, right? So what shuffle join does is it first shuffle the data from both tables to all of the B's based on the join key, right? So it only shuffles once. So let's say if your table A is 5,000 rows and your table B is 1,000 rows, it does not matter how big your cluster is. It's only gonna shuffle the 5,000, right? And evenly, hopefully evenly, distribute that to all of your BE nodes, right? And so the key thing is network and memory usage does not scale with the size of a cluster. It only scales with the size of the data, right? And this makes like shuffle join a much more scalable solution for join operations when compared to broadcast join, right? If your database doesn't support shuffle. And there are some variants too, right? And this is what Sarah supports too. And a lot more optimization can be done. But I just want to pick one as example, and which support bucket shuffle join. So if the join key is the distributed key of the left table, we only need to shuffle the right table, and that makes network incredibly cheap, right? And so the network cost of this is only the data size of B, and the memory cost is only data size of B. Oh, and for this too, I mean, for this, the memory is the B as well, because A, we can do it downstream. We can do it incrementally, right? Yeah. Let's take a step back and look at the bigger picture. So these five are the ones I've talked about. And I think it really emphasized on like how a different compute architecture can actually make a difference just by supporting the shuffle operation, right? It opens doors to many other kind of joint strategies on the network level, on a distributed system, and enables actually truly scalable join operations. And that requires your database to support the join shuffle operation, or else it's not gonna, yeah, those two are not gonna work, right? So you're left with localized joins where you need to pre-configure everything, or broadcast join where it has a lot of limitations, right? Okay, and let's touch a little bit on the query executions as well. And this is mainly the reason why StarRocks is fast overall. This doesn't really contribute to join specifically, but this is the reason why StarRocks is very fast, right? Overall. So StarRocks runs on a columnar storage and has fully vectorized operators. A fully vectorized operator means that every single one of our operators are vectorized. And columnar storage basically means in your storage engine, instead of storing your data in a row format, you store them in a columnar format, right? And what is a vectorized execution? It's that in your memory, instead of processing everything by row, you process them by column, right? And so to put in short, so OLAP operations such as joins and group bys, you always take large chunk of a column, right? Then that's pretty normal, right? So this way we are able to do everything in bigger batches, and so and in memory it's going to be more continuous, right? And it's going to be more CPU cache friendly, and it's gonna be better for CPU branch prediction, and it's especially easy to incorporate SIMD optimizations, and I'm gonna talk about in the next slide. Yeah, and StarRocks is built with C++, so and we're very SIMD optimized, right? So a little explanation on what SIMD optimization is basically we're able to, with SIMD optimization, we can process multiple data points with a single CPU instruction, right? So we touch memory a lot less. Let's say like two, like the image right, like right here, right? And two vectors, we perform a vector addition, right? A multiplication, and with a scalar operation without SIMD, you need to get the data one by one and return the data one by one. So that's 12 memory seeks, and that's 12 instructions. But with SIMD, there's only three, right? Because we do everything in the columnar format, everything in batch. So it makes the execution so much faster, right? And we've done it for as many as the operator we can, including like text parsing, filtering, aggregations, joins, everything is SIMD optimized. And and this is actually why you see the AVX2 instruction set being a requirement, right, for StarRocks to use the vectorization capabilities, because this is a SIMD CPU instruction set, right? Yeah, so that's all, and that's all we covered. On the higher level, we covered why Saras is fast, but there are a lot more details to it, especially in the query planning phase, right? And how do we do join rewarding? How do we do those subquery rewrite? There are a lot more to it, and you can, if you is anything that you're interested in learning or you want to know, let us know on our Slack channel. Join our Slack channel and let us know. Probably gonna do another webinar, or we can write like deep dive blog articles that answers to your question, right? And also take a look at our blog, settledata.com blog, and sign up for Settled Cloud at cloud.settledata.com, and connect with me on LinkedIn. Okay, this is all I have. Let's take a look at some questions. What kind of things should I do to optimize queries? Or does the query planner takes care of it all? Um, yeah, the query optimizer does a lot of things for you. So you don't have to order the joins, like the join tables. It does that for you, right? And even your query is a bit unoptimized, and our query optimizer is going to do that for you, right? Let's see. Oh, yes, this is being recorded. Collect statistic operation, is it run as batch? Wait. Is it run as batch, or when cost-based optimizer is working? If it's in batch, how frequently does it run? This actually I'm not 100% sure. Yeah, I think you need to run a collect statistics command or analyze command in your client, and it's gonna do that ad hocly, right? I'll get back to you with more detail later. Okay. Oh, thank you, Xuan. That's a lot of BEs. That's a lot of SSDs. Okay. So if there's no more question, I think this is it. And connect me on Slack as well, Sida Shen. Oh, you guys talk. I'll wait. So, not VMs, physical machines. I think that's a question for. Okay, it's good to see everybody's making friends. Thank you, Andrew. Thank you. Glad you enjoyed it. Yeah, we're about time, 40 minutes. And if you have any question, do reach out to me on Slack or on LinkedIn. And yeah, have a great day, everyone, or rest of the day or your night. Depends on where you are. Bye.